Hey, stress test financial risk modeling guys. So what I want to do today, I want to talk about stress testing. So and predictions. And predictions using regression. So now let's assume, right, that we have our model, okay, where y is going to be equal to beta I xi plus epsilon. I go through 1 to n, right? So these are the independent variables, and this is a dependent one, okay? And now, and now what I want to do, right, I want to investigate the sensitivity of y to changes in x. So for example, you know, and of course this goes from 0 because we have the intercept at the beginning. So if we do it explicitly, right, y is going to be beta 0 plus beta 1 x1 plus beta 2 x2, yada, 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 beta n xn, right? I think this we already covered gazillion times in class. So now what I want to do, I want to talk about stress testing, okay? And what I want to investigate the sensitivity of y, right? Delta y, the changes in y versus the changes in x. So let's say by how much y will move if x's are going to change by a certain amount. Now this is a little bit different from straightforward predictions, because in a straightforward predictions you just assign, you know, not changes but the level of x, right? And here what I want to do, instead of levels of x, I want to look on delta x1 to delta xn. Okay? So, and this is a little bit different problem. It's not much harder, but it's a little bit different, right? So in this case, right, delta y is going to be the sum of beta I delta xi, right? So I go from 1 to n. So what you see here is that beta 0 is no longer with us. Okay? So beta 0 is omitted from this equation when we talk about changes. So for example, say y equals to 0.5. So y is some equity, right? It has 0.5 as an intercept. And you know, you can assume that these are, returns, but it can be anything you want, right? Plus, let's say 0.7 times y1 plus 0.8 times y2, right? And let's say that delta y1 is going to be 0.01 and delta y2 equals to 0.02, right? So it means that the change from y from today to yesterday or from today to tomorrow, right, is going to be 0.01 and 0.02. So what is going to be the expected change in delta y, right? So it's not delta y, of course, it's delta x. So it's delta x1, delta x1, delta x2, right? So what is going to be the change in y? This is going to be 0.5 times 0.7 times 0.01 plus 0.8 times 0.02, right? So this will be, I think, whatever it will be, I think this is going to be 0.007 plus whatever this is going to be. I don't know what it's going to be. It's going to be 0.016. So together you get, I think 0.023. So this will be your change, right? Now, the 0.5, right, when we look on changes, is a gunner, right? The intercept doesn't participate when we look on changes. Only the betas here participate, okay? This is contrary to what you have when you try to predict. If you try to predict, you say x1 equals, let's say, 1, and x2 equals 2, right? Then y, the level of y, is going to be basically 0.5 plus 0.7 times 1 plus 0.8 times 2. So this is going to be, 1.6 plus 0.7 plus 0.5. So this is going to be 2.3 plus 0.5 equals to 2.8. Okay? Very straightforward. Right? So that's, right, the crux of the matter. Okay? Now, this is actually, okay, this is actually a prediction for one, for one point in time, right? You are actually assuming that you are having, a change in 0.01, 0.02, and this is your expected value, right? Whatever, this is going to be your expected value for the change, and this is going to be your expected value for the prediction. But now the question is confidence intervals. Okay. How do we calculate the confidence intervals for this baby, right? For the changes and for the predictions, right? So first of all, for the prediction, right? Remember that you have the covariance of beta. So, in this case, it will be basically X transpose, X inverse, right, times sigma square, where this is basically going to be your, variance of the residue. So if you assume that you have a normally distributed, prediction, right, that this is all normally distributed, then once again, you have only two parameters you need to worry about. It's your variance, it's your covariance matrix for the multi-normal distribution and for the expected value. The expected value for the prediction you already found, right? This is going to be basically, you just substitute x0 inside. What is going to be, right, our variance, right? So there are two parts to the variance. The first part is coming from the variance of beta, and this is going to be basically x0, right, times c beta times x transpose. Now, this is your, c beta is this guy, so you're going to get x0, x transpose, x inverse times x0 transpose times sigma square, right? And the second portion is going to come from the residual, right? So this is going to be plus sigma epsilon square. Okay? And now you are having that this is going to be sigma epsilon square, and here you have 1 plus this guy. Okay? So your standard deviation is going to be sigma epsilon times square root of these guys times x transpose. Okay? Very straightforwardly. Nothing, nothing fancy. Now, if you want to generate confidence intervals, so once again, you have a threshold. And now if you have enough n, right, we said in class that this is going to be, that this is going to collapse to 0 because this is proportional to 1 over square root of, to 1 over n, right? So the only thing, if you have a lot of, observations, is coming from this guy, right? So if n goes to infinity, or if you have a lot of observations, this is going to be just sigma epsilon, okay? And that's the one, and that's what I use in class, right? On many occasions, I use this approximation. Now, if you want a confidence interval, let's say that you have a threshold. Let's say for 95 percentile, you have 164, right? So what you're going to get here, you're going to get basically, your prediction, which is, basically, your y predicted, plus minus 164 times this guy. Times not this guy, sorry. Not this guy, but this guy, right? So, pretty straightforward, and you did it on the test, and you did it all nicely. But now, what's going on with the delta y? So the first thing you want to notice, right, that the intercept doesn't participate. So the betas, right, which are going to contribute are going to be just the betas, but without without the intercept, right? So then, right, you just remember that we can actually write the covariance matrix as C beta as the Cx inverse, where the Cx inverse is the covariance matrix of all the x's, but without the intercept, right? Without the ones that we get, that we have, in the beginning. Then we multiply by sigma, and then we, by sigma square, and then we divide by n. Okay? So this guy is going to come from the beta. Now we also have, a residue, and that's where the thing's getting a little bit interesting. Because once again, right, it depends how you shock. If you assume an instant shock, that there is no time component. So you basically look at the shock today and you say, okay, I know my x's today, I'm going to instantly shock them. There is going to be no, right, there is going to be no residue because the residue is going to go away. It's the same residue, okay? It's the same residue because you shock xi here and you have the same vector, right? So if you have the same vector, whatever it is, when you subtract those two things, it will cancel. It will cancel. There is nothing. There is going to be no, no epsilon, right? So then your sigma, right, will be just this guy. This is going to be your covariance, right? This is going to be your covariance. Now, and this is kind of important. If you shock it, let's say in the future, okay, this epsilon is unknown. You don't know this epsilon. Let's say you shock it today, you want to observe the change from tomorrow to a month from now. So you say, okay, I know my x's tomorrow, and then in a month something will change, right? So you have then two epsilons here. Two epsilons, right? It means that your formula, right, that what you need to look on, when you look on epsilon, you need to look on epsilon 1 minus epsilon 2. What is going to be the variance of epsilon 1 minus epsilon 2 if you know that epsilon 1 and epsilon 2 have the same distribution? Is going to be basically sigma epsilon times 2. If you do the calculation, right, the variance of epsilon 1 minus epsilon 2 is equals to variance of epsilon 1 minus 2 times covariance of epsilon 1, epsilon 2, plus variance of epsilon 2. But the covariances goes away because they are independent, right? So you get sigma epsilon times 2. So in this particular case, if you shock them in the future, right, and you don't know, you don't know your epsilons on both, tomorrow and, and let's say after tomorrow, okay, you are going to get the following formula. And that's the formula that I did in class. Is going to be Cx inverse, right, times sigma square divided by n, right? And then you want to multiply by your change. Okay? This is going to be, the stuff that comes from the beta, right? Because, because it's exactly the same as a prediction. But then you are going also to have the stuff that is coming from, from the epsilon, which is going to be sigma epsilon times square root of 2. Sigma epsilon times 2. So you're overall going to be basically sigma epsilon times square root of 2 plus, right, delta x Cx inverse times sigma divided by n. And this is going away, right, times delta x transpose. Okay? So this guy, right, will have two features. It will have a 2 and it will have this. Now, this 2 is a little tricky. Because why this 2 is tricky, right? Because when n goes to infinity, this is what is going to be dominant, right? So then you're going to get that your confidence interval sigma epsilon times square root of 2. But remember, now this sigma epsilon is not measured against your prediction. This sigma epsilon square root of 2 is measured against your, your changes. So then this variance will be actually enlarged. Okay? So that's something that you need to take into account. When you do those kind of, changes, right? When you do those kind of changes, if something moves, okay, you're going to have, this kind of confidence interval, sigma epsilon times square root of 2, okay? When you have a lot of observations. Because we don't know what will happen in the future. Okay? So that was it, and I hope that you enjoyed the video. I hope that this puts the saga of stress testing and predictions into bed. And, I'll see you in class. Thank you very much and have a great day. Bye.